In this video, I plan to show how a helicopter drive system transfers power from the engines to the rotors. There are multiple stages of gear reduction and direction change involved. This drive system reduces the speed of rotation from 14,000 RPM at the engine to 256 RPM at the main rotor. And the main rotor has a 95-degree direction change from the engine output to the rotor input. The tail rotor in this model rotates at 1400 RPM. These rotation speeds are representative of typical large turbine-powered helicopters. The overall gear reduction from the engine to the main rotor is 55-1. Because there are so many components needed to create this gear reduction and direction change, it'll be easier to visualize if I first hide all of the components and then bring them back one at a time to show the gear reduction and function of each component. I'll start by hiding the flight controls and the hydraulics. Then I'll hide all of the drive gears, tail rotor gears, tail rotor shafts, and the tail rotor itself. Finally, I'll hide the engine cases so you can see both the gas generator and the power turbine. Helicopters generally use turboshaft engines with two rotating spools. The front spool is the gas generator and the aft spool is the power turbine. These spools are not mechanically connected. The gas generator converts air and jet fuel into energy in the form of a high-velocity flow of expanding hot gas. The power turbine extracts power from this flow of hot expanding gas, and this is the only part of the engine that is mechanically connected to the drive system. The gas generator in this model turns at 14,000 RPM, and the power turbine turns at 12,800 RPM. These speeds are representative of actual turbine engines, although the animation appears slower because I've slowed down the playback speed. For better visualization of only the mechanical path to the rotor, I'll hide the gas generator spool for the remainder of this video. And now we'll start connecting the power turbine shaft of the engine to the rotor with various drive system components and explain the gear reductions as we go. The flexible couplings at the front of the power turbine shafts are there to allow for minor misalignments of rotating machinery. Misalignment is expected during flight of the helicopter. The 28-tooth pinion gears at the front of the power turbine allow a connection to the next reduction stage of the drive gears. For now, these parts have not gone through any gear reduction, so everything here is rotating at 12,800 RPM, the same speed as the power turbine shaft. The next part is a 56-tooth gear attached to a one-way clutch. This assembly is called a freewheeling unit, and it serves two purposes. The gear part of the freewheeling unit provides a gear reduction, and the clutch part automatically disconnects a failed engine from the drive system. Without the freewheeling unit, a failed engine would drag the rotor system and make it incapable of an engine-out auto-rotation. This is an important safety device as it allows the helicopter to auto-rotate and land safely following an engine failure. The 56-tooth gear on the freewheeling unit, driven by a 28-tooth pinion, gives a gear reduction of 56-28 or 2-1. Since the power turbine turns at 12,800 RPM, the freewheeling unit now turns at 6,400 RPM. The next step in the gear reduction comes from two 28-tooth gears driven by each of the freewheeling units and powering a 56-tooth common bull gear. This is where the power output of two engines is combined into one input to the rest of the drive system. Because the 56-tooth bull gear mates with a 28-tooth pinion, this gives an additional 2-1 gear reduction. The bull gear output is 6,400 over 2, or 3,200. In front of the bull gear, there's a 28-tooth bevel gear, and this mates with a 70-tooth bevel gear at a 95-degree angle. This gives a 5-degree forward tilt to the rotor mast, and this is a common feature on large helicopters. The 5-degree forward tilt gives a level fuselage attitude in forward flight. A 28-tooth gear mating with a 70-tooth gear gives a 2.5-1 gear reduction, and the main bevel gear is now turning at 3,200 over 2.5 or 1,280 RPM. At this point, the combined gear reductions have slowed the animation so much that it's hard to visualize motion, so I'm going to speed up the animation. Keep in mind, I'm not changing any of the gear ratios. I'm only changing the speed of the playback. The next step in the drivetrain is a planetary gear set. I'll start by adding a 24-tooth sun gear, and then 4 36-tooth planet gears. These 4 planet gears turn inside of a 96-tooth ring gear. This arrangement gives a 5-1 reduction, and the output power comes from the 4 planet gears. To access this power, we'll need a device called a planet carrier that connects the 4 planet gears directly to the rotor mast. The input rotation to the planetary sun gear was 1,280, so after a 5-to-1 gear reduction, we're left with 1,280 over 5, which is 256. This is the final gear reduction, and the main rotor speed is now 256 RPM. The tail rotor is driven from the same gear set that drives the main rotor. Looking at the back of the main bull gear, there are 3 16-tooth gears and a final 30-tooth tail rotor drive gear. The multiple 16-tooth gears are idle gears, and they serve the purpose of lowering the tail rotor drive shaft to an appropriate waterline on the helicopter. The 16-tooth input gear is driven by the bull gear that turns at 3,200 RPM. Connecting a tail rotor drive shaft with the 30-tooth gear gives a gear reduction of 30 to 16, or 1.875 to 1. The rotation speed of the tail rotor drive shaft is 3,200 over 1.875, or 1,700 RPM. The tail rotor drive shaft is a 3-piece drive shaft with flexible couplings along the length of the shaft. The tail rotor drive shaft has an intermediate gearbox that changes the direction of the drive by 120 degrees. The 25-tooth input meshes with the 30-tooth gear to reduce the RPM of the intermediate drive shaft. The gear reduction here is 30 to 25, or 1.2 to 1, so the intermediate drive shaft turns at 1,700 over 1.2, or 1,400 RPM. The final set of gears in the tail rotor drive system are 2 25-tooth bevel gears. Because both gears are the same tooth count, this doesn't change the RPM of the tail rotor from that of the intermediate drive shaft. These gears are beveled to give a 20-degree upward cant to the tail rotor, and this serves the purpose of providing some lift from the tail rotor in addition to the tail rotor's main purpose of countering main rotor torque. If you made it this far, I'd like to thank you for watching as we went through how engineers take the high-speed output of a turbine engine and transfer that power to the relatively slow rotation speeds of helicopter rotors. When I started this channel a little over a year ago, I had no idea that so many of us geek out on how machines, helicopters in particular, operate. I realize 10K subscribers and 3 million views is relatively small by YouTube standards, but it's still kind of a thrill for me that so many of you are interested in this content. I sincerely thank you for watching, and I hope to see you next time.